Alright guys, so this is chapter 9, Chemical Equation Calculations. This is a continuation of chapter 8 and 7. So here we're putting what we learned from chapter 7 about balancing equations and what we learned about chapter 8, which was the idea of the mole, and we're putting them together and seeing how we can use the idea of the mole with chemical equations. So pictured here on the slide, we have a chemical equation, and we can verify that it is balanced right here. Yep. So we can see that it is NO, which is nitrogen monoxide, plus O2, which we know is elemental oxygen because oxygen is diatomic, makes NO2, which is nitrogen dioxide gas. And we can see the coefficients here. So the coefficient in front of nitrogen monoxide is 2. There's nothing in front of the oxygen, which means it's a 1. And then there's a 2 in front of the nitrogen dioxide. And so we learned about balancing, how to balance, all that good stuff in chapter 7. So what do those numbers mean? What does that 2 in front of the nitrogen monoxide mean? What does that 1 in front of the oxygen mean? What does that 2 in front of the nitrogen dioxide mean? Well, what those numbers represent are what we call molar ratios. They are essentially the amount of moles of each one of those, or the ratio of moles of each one of those. So for example, in order to make this reaction happen, we need to have 2 moles or 2 molecules of nitrogen monoxide reacting with 1 molecule of oxygen gas, and that'll give us 2 molecules of nitrogen dioxide. Now remember guys, this is a ratio, so it could easily be 4 nitrogen monoxides plus 2 O2s will give us 4 nitrogen dioxides. So here we are breaking it down. What are the different ways we can interpret these coefficients here? So again, these are molar ratios, but what is a mole but the word for just a whole bunch of molecules, right? To be specific, remember 1 mole is 6.02 times 10 to the 23rd molecules. So these are molar ratios, or these are molecular ratios, but they absolutely are not mass ratios, guys. I cannot stress this enough. Make sure you make an important note here. These stoichiometric coefficients, as we call them, these coefficients here in the front, they absolutely cannot be used with mass units. Remember, the mass units are things like grams and such. So they can represent molecular ratios. 2 molecules of nitrogen monoxide will react with 1 molecule of oxygen to give 2 molecules of nitrogen dioxide. And remember guys, these are ratios. It can be any ratio of 2, 1, 2. It could be 10 molecules of nitrogen monoxide react with 5 molecules of oxygen gas to give us 10 molecules of nitrogen dioxide, or it could be 6, 3, and 6, or any ratio that simplifies down to 2, 1, and 2. So it could be 2 molecules, it could be 2,000 molecules of nitrogen monoxide reacting with 1,000 molecules of oxygen to give 2,000 molecules of nitrogen dioxide. Again, notice here how we're still keeping the 2 to 1 to 2 ratio. And again here, 12.04 times 10 to the 23rd molecules, 6.02 times 10 to the 23rd molecules, and 12.04 times 10 to the 23rd molecules. Again, keeping with that 2, 1, 2 ratio here. So we now know that this balanced chemical equation means 2 moles of nitrogen monoxide gas react with 1 mole of oxygen gas to produce 2 moles of nitrogen dioxide gas. And remember guys, these are ratios. It doesn't mean that we're going to need 2 moles 1 mole and 2 moles every time, all it means is that the ratio of moles between nitrogen monoxide, oxygen, and nitrogen dioxide has to be 2, 1, and 2. So here's another way to look at it. We have a general chemical equation down here. 2A plus 3B yields 1C and 2D. A, B, C, and D are just placeholders. And we can assume that this is balanced. So we have a coefficient of 2 in front of the A, a coefficient of 3 in front of the B, a coefficient of 1 in front of the C, and a coefficient of 2 in front of the D. So what do those ratios represent? Well, they can represent molecules. I could have a ratio of molecules that is 2 to 3, 2 to 3 to 1 to 2. Or I could have a ratio of moles of that same number, or if all of these compounds are gases, it is the ratio of, it could be the ratio of the volume as well. Remember back last chapter, chapter 8, when we learned about the idea of molar volume. Essentially what that means is that if the gases are under the same set of conditions, the same set of pressure and temperature conditions, what that means is that 1 mole of the gas, it doesn't matter what the gas is, will take up that same amount of volume. And so for that reason, these can be volume coefficients as well if we are talking about an all-gas phase reaction. So going back to the law of conservation of mass that we learned way back at the beginning of the semester, and we touched on it again in chapter 7 as to why we balance chemical equations in the first place. The law of conservation of mass says that matter is neither created nor destroyed during the process of a chemical reaction. That's why we have to count and make sure that we have the same number of the same kinds of atoms on both sides of the arrow. That's why we balance, right? Just a quick check. 2NO means I have 2 nitrogens. I have 1, 2, 3, 4 oxygens on the reactant side. 2NO2 means I have 2 nitrogens and 4 oxygens on the product side. So everything looks good here. And remember these coefficients, the 2, the 1, and the 2 represent molar ratio. So we can just make up some numbers. Let's say we have 2 moles of nitrogen monoxide gas. Based on these ratios, we know that 2 moles of nitrogen monoxide gas will react with 1 mole of oxygen gas to produce 2 moles of nitrogen dioxide. Let's find the molar mass of these guys. Remember, the molar mass comes from the periodic table. Nitrogen is 14.01, oxygen is 16. Add them up, you get the molar mass of nitrogen monoxide as 30.01. O2 is 32, and nitrogen dioxide is 46.01. And then this is just how many moles we have. Remember, a molar mass means grams per moles. So if I have 2 moles of nitrogen monoxide gas, I have 2 times 30.01 grams, which means I have 60.02 grams. Taking the calculations through for the rest of my compounds, we see that the 2 moles of nitrogen monoxide plus the 1 mole of oxygen is a total mass of 60.02 grams plus 32.00 grams, which gives us a total mass on the reactant side of 92.02 grams. 2 moles of nitrogen dioxide gas on the product side gives us 2 times 46.01, which is that same 92.02 grams. Mass is conserved. So in the previous slide, I mentioned the idea that these stoichiometric coefficients, and remember the stoichiometric coefficients are what we call these numbers here in the front. For hydrogen it's 1, for chlorine it's 1, and for HCl gas it's 2. So we learned that these are molar ratios, but because all of my compounds here are in the gas phase indicated by this little g, These coefficients can also be volume ratios as well. Now you can only do this for an all gas phase reaction. So we could say 1 liter of hydrogen gas combines with 1 liter of chlorine gas to make 2 liters of hydrogen chloride gas. Just a little note here, guys, HCl, AQ, we remember this from chapter 6 as being called hydrochloric acid. What makes it hydrochloric acid is the fact that it's aqueous. If it's HClG, if it's a gas, it is no longer hydrochloric acid. Now it is called hydrogen chloride gas. So when talking about STP, remember STP was those conditions 0 degrees Celsius, which was 273 Kelvin, and 1 atmosphere of pressure. Pressure is at 1 atm, and we'll learn more about what that means in chapter 10. We learned that 1 mole of a gas, any gas, it doesn't matter what, was 22.4 liters. And from there we sort of extrapolated out that it doesn't matter what the temperature or the pressure of our gas is, so long as all of our gases, here we have 3 different gases, the same gases from the previous slides, nitrogen monoxide, oxygen, and nitrogen dioxide. So long as all 3 of those gases are exposed to the same temperature and pressure conditions, 1 mole of each gas will have the same volume, whether that volume is 22.4 liters at STP or a different number under a different set of conditions. And so for that reason, we can use the molar coefficients as volume coefficients. So rather than saying 2 moles of nitrogen monoxide gas react with 1 mole of oxygen gas to give us 2 moles of nitrogen dioxide gas, we can use liters. And remember, these are ratios. So I could just as easily say 8 liters of nitrogen monoxide gas will react with 4 liters of oxygen gas to give us 8 liters of nitrogen dioxide gas, as long as we keep that ratio of 2 to 1 to 2. So let's check our understanding here. So if I have 10 moles of nitrogen monoxide gas, if I have 10 moles here of this guy, and excess oxygen. So what this word excess means is it means we have all that we need and then some. So assuming I have as much oxygen gas as I could ever need, and I have 10 moles of nitrogen monoxide gas, how many moles of nitrogen dioxide gas will we get? What do you guys think? We'd get 10 moles. Where did I get that number from? Well, by looking at the ratios, right? So the ratio, or the coefficient in front of nitrogen is 2, of nitrogen monoxide is 2. The coefficient in front of nitrogen dioxide is also 2. So because these coefficients are the same, what that tells us is that however many moles of nitrogen monoxide I will have that same amount of moles of nitrogen dioxide gas. We have a conversion factor here. So we can use the idea of the molar ratio as a conversion factor. And this is some of the work that you guys did with your pre-lab, post-lab experiment 12, pre-lab and post-lab experiment 15. And here's how we would set it up. So unit conversion, same 3 questions all the time. What unit do I have? What unit do I want? And what is the relationship between the 2 of them? So we have 10 moles of nitrogen monoxide gas. What unit do I want? I want moles of nitrogen dioxide gas. Do I have a relationship between moles of nitrogen dioxide gas and moles of nitrogen monoxide gas? I do. That relationship uses the stoichiometric coefficients. Here's how we would set it up. So moles of nitrogen monoxide gas is what I have, so I'm going to put moles of nitrogen monoxide gas on the bottom of this conversion factor to cancel it out. And I will put the unit that I want to turn it into, which is moles of nitrogen dioxide gas, on the top. Remember, guys, when setting up conversion factor, it's always easier to start with the units and then plug in the numbers later. So what are those numbers? What are the numbers that goes in front of moles of nitrogen dioxide gas? What is the number that goes in front of moles of nitrogen monoxide gas? Those numbers are the stoichiometric coefficients from the balanced chemical equation. So this is where everything sort of comes together. You need to know the names so you can have the proper formulas. You need the proper formulas so you can balance the chemical equation properly so you can do these calculations correctly. So we have a correctly balanced chemical equation here. So I put the coefficient 2 from this 2 and another 2 down here from this 2. Well, 2 divided by 2, that's just 1, right? So moles of nitrogen monoxide cancel out, and we end up with 10 moles of nitrogen dioxide gas. What about if this number was a more difficult number? Say it was 3.75 moles. How would the problem be different? Well, 3.75 times 2 divided by 2, still 3.75. How many liters of nitrogen monoxide would you need to completely react with 5 liters of oxygen gas? So when I do this problem up top here, I'm going to get a little cramped. So remember, because this is an all gas phase reaction, we can use those coefficients as volume coefficients as well. So what do we have? We have 5 liters of oxygen gas. What do we want? We want liters of NO. So how do we get there? So liters of oxygen gas goes on the bottom. We would put liters of nitrogen monoxide gas on the top. And the same coefficients we plug in. 2 on top for nitrogen monoxide, because that's the coefficient in front of that. 1 on the bottom, because that's the coefficient in front of the oxygen. Liters of oxygen and liters of oxygen cancel. So we end up with 5 times 2 over 1, which is 10 liters of nitrogen monoxide gas. So investigating this a little bit further and using what we learned on the previous slide, we can see that all of these coefficients can be used to be representative of different conversion factors. And there's a bunch of different ways we can write it, any which way we could possibly need the relationship between nitrogen to oxygen, or oxygen to nitrogen, or nitrogen to nitrogen monoxide, etc., etc., etc. So we have all the possible molar relationships between all of the chemicals in our reaction, assuming we have a correctly balanced chemical equation, which we do. Okay, so let's try it out using this new chemical equation. So how many moles of oxygen react? Okay, so this is what we want. We want moles of oxygen will react with 2.25 moles of nitrogen. So before we can answer this question, we need to verify that we have a balanced chemical equation. So quick check, 2 nitrogens on the reactant side, 2 oxygens on the reactant side, 2 nitrogens and 2 oxygens on the product side. Okay, this is balanced. What do we have? We have moles of nitrogen. So what is the relationship between what we have and what we want? To see that relationship, we need to look for the coefficients of the balanced chemical equation. So the coefficient in front of nitrogen is 1, coefficient in front of oxygen is 1. So we use this relationship, 1 mole of nitrogen over 1 mole of oxygen. Setting up our problem, 2.25 moles of nitrogen times moles of nitrogen on the bottom, moles of oxygen on the top. Moles of nitrogen and moles of nitrogen cancel out, leaving us with the answer converted to moles of oxygen. And it's the same number because it's a 1-to-1 ratio. So let's look at a slightly more difficult problem. If you had to, by the way, could you name all of these chemicals? Go ahead, take a minute, try it out. What's this first one called? What does this mean? This first one is called calcium chloride. AQ means aqueous, so here we are talking about calcium chloride dissolved in water. What is this second chemical called? That's silver, that's nitrate, so this is silver nitrate, and again, aqueous dissolved in water. What about this guy? That guy is called silver chloride, and here it has a little S, which means it's a solid. So does this guy, what special name does this guy get? Before we answer that question, we need to figure out what reaction type do we have. So based on the two reactants, what reaction type does it look like we have here? We have two aqueous ionic compounds as reactants, which means we have a double replacement reaction. So we are mixing together two aqueous things. A solid appears. That solid is called the precipitate, abbreviated PPT. And finally, this last chemical here, this guy is called calcium nitrate. So you can treat these chemical equations, treat them as recipes, right? 1 part calcium chloride, 1 mole calcium chloride, when mixed with 2 moles of silver nitrate, you mix them up real good, and here's what you get. You get 2 moles of silver chloride and 2 moles of calcium nitrate. So, in the previous slides, we were working with moles, but that's not terribly realistic. In the lab, what unit are we always measuring things in? In the lab, we're always measuring things in grams or things in liters or milliliters. We very rarely measure things in moles in the lab. So, for example, say you want to do this chemical equation in the lab. And you go ahead and you get yourself 2.000. By the way, guys, how many sig figs is this? It's going to be 4 sig figs. So you get yourself 2.000 grams of calcium chloride and excess silver nitrate, so we just assume we have enough. How much silver chloride do you expect to get? So a little sneak preview here, guys. This thing that we're about to talk about, this is called the theoretical yield. Theoretical yield, abbreviated TY. Theoretical yield tells us the maximum amount of product we can expect to get, assuming this chemical reaction goes 100% as planned. So the theoretical yield represents the maximum allowed amount of product that you can possibly get. And that is determined by these chemical equation calculations. So as always, we start with a balanced chemical equation. So you have 2.00 grams of calcium chloride. You want to know how many grams of silver chloride you can get. So remember in the beginning of this presentation, I said these coefficients out front here, they are volume coefficients for gases, and they are molar coefficients for molecules, but they are absolutely not mass coefficients. So we cannot say, oh, well, there's a 1 in front of calcium chloride and a 2 in front of silver chloride, so 2 grams of calcium chloride will give me 4 grams of silver chloride. We can't say that. That is wrong. What we have to do first is we have to convert everything to moles. The only way we can move from one chemical, calcium chloride, to another silver chloride is if we are in the unit moles. Okay, so we're going to click the slide here. 2 grams of calcium chloride, we need to convert that to moles. How do we do that? Let's click the slide. Okay, so we use the molar mass of calcium chloride. And again, this comes from our friend, the periodic table. Click the slide. So where did this come from? And why are we doing it? Okay, so we understand what's going on here with this first conversion factor. The purpose of this first conversion factor is to cancel out the grams of calcium chloride to get it into moles of calcium chloride. And we know the grams to moles, that ratio of calcium chloride from the periodic table. We add 1 calcium, which is 40.08, plus 2 chlorines, each chlorine being 35.45, so 2 chlorines is 70.90. Add them up, we get 110.98 as our molar mass. But we're not done being in moles of calcium chloride. We need to get to moles of silver chloride. So we do that using the molar conversion with the molar ratios. So I have moles of calcium chloride up top. So to cancel that out, I put moles of calcium chloride down bottom here and moles of silver chloride on top because that's what we want. And the numbers come from the balanced chemical equation. So the 2 in front of silver chloride up here becomes that 2 there, and the 1 in front of calcium chloride becomes that 1 there. So here is where we would stop, right here, if we wanted moles. But if we want to get to mass, what's the next step? Again, ask yourself those same 3 questions. What unit do I have? What unit do I want? And what's the relationship between the 2 of them? So right now, we have moles, specifically moles of silver chloride. What unit do I want? We want mass, or grams of silver chloride. What is the relationship between moles and mass? Well, it's the molar mass, again, which comes from your periodic table. Click the slide. So we put moles of silver chloride on bottom to cancel out with the moles of silver chloride up here. We take the molar mass of silver chloride, which is 143.22, and now we multiply this whole thing across, do a quick sig fig check, 4 sig figs here, 5 here, 5 here, which means I should end up with the final answer of 4 sig figs. So the reason why I didn't count the sig figs of this 2 and this 1 here in this conversion factor is because, remember, we don't count sig figs for exact conversions. Advance the slide, and we get our answer in 4 sig figs of 5.116. So theoretically, if I have 2 grams of calcium chloride, the most amount of silver chloride I should get is 5.116. This, again, is our theoretical yield, our TY. Theoretical yield. Slide again. So we're making it a little bit more complicated now. What do you do if we have 2 grams of calcium chloride and 2 grams of silver nitrate? So in the previous problem, we just specified that we had the 2 grams of calcium chloride and we assumed that we had as much silver nitrate as we needed. Now you can't assume that anymore. So when you are given amounts of both reactants, like we are here, so this concept that we're about to do is called the idea of the limiting reagent or limiting reactant. So what it depends upon is which chemical is used up first, which reactant runs out first. So here's how we do that. So what we need to do is essentially we need to break this problem up into 2 separate problems. For the first problem, what I'm going to do is figure out how much silver chloride I can get with 2.00 grams of calcium chloride. That's problem 1. And then we're going to forget that, and then we're going to do problem 2. And problem 2 is going to be how many grams of silver chloride I can get, assuming I have 2 grams of silver nitrate. And then we're going to compare those two answers. Let's click the slide here. So here we have our previous calculations that we did in the previous slide, showing us that 2 grams of calcium chloride gives us 5.116 grams of silver chloride. Let's click the slide. And so rather than doing it step by step here, we just have it all at once. So 2 grams of silver nitrate, in order to convert it from silver nitrate to silver chloride, remember we need to be in moles. So we need to convert this grams of silver nitrate to moles of silver nitrate using the molar mass. Grams on the bottom cancels out with grams on the bottom. Now we are in moles of silver nitrate. So moles of silver nitrate on the bottom here cancels out with this moles of silver nitrate. Put moles of silver chloride on top. The 2 to 2 molar ratio comes from the coefficients here, 2 and 2. Then we multiply by the molar mass of silver chloride, just like we did here in this last step. And so what we're doing is we are comparing the two amounts of products that we can get. So if I have 2 grams of silver nitrate, I'm going to get 1.687 grams of silver chloride. If I have 2 grams of calcium chloride, I'm going to get 5.116 grams of silver chloride. So the number that we go with, the numbers that we go with are the numbers that give us the least amount of product. So in this case, that would be this bottom calculation here. So the reason for that is what this means is that this 2 grams of silver chloride is going to get used up before the 2 grams of calcium chloride does. Once this 2 grams of silver chloride gets all used up, the reaction stops because you're missing a reactant now. And so the silver nitrate here, the one that caused the lesser amount of product, the silver nitrate, this we consider our limiting reactant or our limiting reagent. And the amount of product that we can get according to our limiting reactant or limiting reagent, in this case, this one is the correct theoretical yield. So this top example here, once we realize that this is not the limiting reagent, we just forget all about it, cross it out, put it out of our minds entirely. And here, in this case, calcium chloride is what we call the excess reagent. So the limiting reagent is the one that gives you the less amount of product. It's the one that runs out first. And the other chemicals in the reactant side are the excess reagents. So excess reagent, calcium chloride, limiting reagent, silver chloride, or silver nitrate. And so the purpose of this last calculation here is to demonstrate that if I have 2 grams of silver nitrate, it's going to react with 0.996 grams, or it'll make 0.996 grams of calcium nitrate. So we can point it to either product. The thing is that when you're doing these problems, for the limiting reagent problems, you need to make sure that you're converting both of your reactants to the same product. So notice how in the first 2 examples we converted calcium chloride to silver chloride, and we converted silver nitrate in the second example again to silver chloride. So in order to have a valid comparison, you need to be converting to the same product. So let's try this example. So FeO, this first reactant here. What's it called? I'll give you guys a second. How many of you guessed that it was called iron 2 oxide? This is called iron 2 oxide. And that L means that it's a liquid. Second reactant, aluminum. First product, iron. What about this guy? What's this guy called? Our last chemical here. This is called aluminum oxide. No numbers, just aluminum oxide. So let's say we mix in a big old pot 25.0 grams of iron 2 oxide and 25.0 grams of aluminum. How much molten iron, so that is how much of this chemical here, are we going to get? So remember our steps. Our steps are to do each reactant separately and then compare them once you have the answers. So the first thing we're going to do is we're just going to convert our 25 grams of iron 2 oxide to the product of interest, which we were told was iron. So molar ratio between iron 2 oxide and iron is 3 to 3. That's where these numbers come from, that 3 and that 3. So first step, we have grams, we want moles, use the molar mass, moles on top, grams on bottom. Second step, convert from moles of iron 2 oxide to moles of iron. So iron 2 oxide on the bottom, iron on top. Last step, convert from moles of iron to grams of iron using the molar mass, grams on top and moles on bottom this time. So my 25 grams of iron 2 oxide will give us 19.4 grams of iron. Now let's try it with the aluminum. So I have 25 grams of aluminum. First step, to get from aluminum to iron, remember we have to be in moles. So we convert grams of aluminum to moles of aluminum. Go to the periodic table, molar mass of aluminum is 26.98. Grams on the bottom here to cancel out with grams, moles on top. Then we use the molar ratio of 3 moles of iron to 2 moles of aluminum, which come from the balanced chemical equation. Moles of aluminum on bottom, cancels out with moles of aluminum here. Now we're in moles of iron, and then finally moles of iron to grams of iron gives us 77.6 grams of iron. So let's compare those two numbers that we just got. So comparing the results, the 25 grams of iron 2 oxide gives us 19.4 grams of iron, whereas the 25 grams of aluminum will give us the 77.6 grams of iron. Which one is the limiting reactant? The limiting reactant is the one that gives us the smallest amount of product. So that would be our iron 2 oxide right here. This is our limiting reactant, the iron 2 oxide, which means my theoretical yield is 19.4 grams of iron. And so we forget entirely about this one here. This one no longer means anything to us. Just cross it off. So iron 2 oxide is limiting, and the aluminum is the excess reactant. So in the post lab for 15, you guys did some percent yield calculations. So what percent yield is defined as actual yield divided by theoretical yield. So actual yield is the amount of product that you actually get. So you go into the lab, you do the experiment, you weigh your product. How much did you actually get at the end of the day? That's your actual yield. So the actual yield must be given to you. You cannot calculate it. It is something that has to be given to you, either because someone told you what it was or because you went into the lab and measured it yourself. The theoretical yield is calculated. This is what we've been doing this entire chapter, this theoretical yield here. So this is calculated based on the chemical equation. So the percent yield is defined as the actual yield divided by the theoretical yield. Now, sometimes you can end up with an actual yield that is higher than your theoretical yield, which will result in a percent yield of above 100%. Sometimes that can happen. And in fact, that is what happened for lab 15. Usually the reason for that is because there's still some water in your product that you haven't accounted for. Or there's some other impurities in your product that are adding mass that you're not accounting for. But typically, percent yields have to be 100% or less because you can't create matter from nothing. So let's do a quick percent yield calculation here. So suppose we do this reaction, and I'm sure you can guess what I'm going to ask. First of all, is it balanced? Second of all, what type of reaction is this? Third of all, what are the names of everybody? So is it balanced? Quick glance, yes, it is balanced. Okay, make sure you can convince yourself that it's balanced. Second question, we have two aqueous ionic compounds. This is a double replacement reaction. Third question, what's everybody called? First chemical, copper 2 nitrate. Second chemical, sodium carbonate. Third chemical, copper 2 carbonate. And last chemical, sodium nitrate. So suppose a student goes in the lab and performs this reaction and actually gets 0.857 grams of the copper 2 carbonate product. So this is our actual yield up top here, actual yield. But according to the limiting reagent calculations, the theoretical yield should have been 0.988 grams. What is the percent yield? So we take the actual yield, 0.875, divided by the theoretical yield, 0.998, times 100%, we get 88.6% as our percent yield. So let's take a look at this practice problem. 175 grams of iron 3 oxide react with 37.5 grams of aluminum in the reaction below. So I give you the reaction and I ask you a couple questions about it. First question, is the reaction balanced? So no, it's not. We balance it by putting a 2 in front of the aluminum and a 2 in front of the iron. Next question, what is the mass of iron produced? So recall in these limiting reaction type questions, we need to figure out how much iron is produced according to both of the products given. So we really need to do this problem twice. Once, using the 175 grams of iron 3 oxide, and a second time using the 37.5 grams of aluminum, and see which number is smaller. And the number that is smaller will be the limiting reactant. So let's start with the 175 grams of iron 2 oxide. Iron 3 oxide. So we have 175 grams of Fe2O3, which is iron 3 oxide. We convert that to moles. So 1 mole Fe2O3, and you'll see why I'm writing the chemical names down in a minute. So the molar mass of iron 3 oxide is 159.69 grams, which comes from the periodic table. 159.69 grams Fe2O3 times. So now we need to convert this moles of iron 3 oxide to moles of iron, because we can see that the grams of iron 3 oxide cancel out with grams of iron 3 oxide here. We can see that easily because we wrote the chemical names. So our mole ratio is 2 moles of iron to 1 mole of iron 3 oxide. And so a mole of iron 3 oxide, what color? Mole of iron 3 oxide and mole of iron 3 oxide cancel. But we wanted the mass of iron, and mass is grams, so we need to convert this quantity into grams. Molar mass of iron is 55.85 grams iron per 1 mole iron. And again, that cancels out, leaving us in the unit of grams of iron, which is where we want it to be. So because this reaction, because all these numbers, the amount of sig figs we are limited to is 3, the answer here in 3 sig figs is 122 grams of iron. So now we need to figure out how much the aluminum gets it and compare those two numbers. So let's divide our page.
and do it again with the aluminum. So we start exactly the same, 37.5 grams of aluminum. We convert that to moles using the molar mass of aluminum, which is 26.98. 1 mole of aluminum on top, 26.98 grams of aluminum on the bottom, times 2 moles of iron on top, 2 moles of aluminum on bottom, and again, these numbers are coming from the stoichiometric coefficients, times 55.85 grams of iron over 1 mole of iron. And we can see grams of aluminum cancel, moles of aluminum cancel, moles of iron cancel, giving us in 3 sig figs the answer 77.6 grams. We can see that this number, 77.6 grams, is the smaller number, so this is the number that we want to use, so that's the answer. So we forget about all of this, none of this matters anymore. So because the chemical that gave us the smaller number of iron was aluminum, that means aluminum is our limiting reagent. So the actual yield is 50 grams. What is the percent yield? Recall that, I erase this stuff because we don't need it anymore. Recall that percent yield is actual yield divided by theoretical yield. So what we do is we take our actual yield, and remember the actual yields always have to be given to you, and we divide it by the theoretical yield, which we got from our calculations. So 50.0 grams divided by 77.6 grams times 100% in 3 sig figs, that gives us 64.4%. All right, guys, that is it for Chapter 9. Any questions, please let me know via email.